When we started out, we talked about defining the behavior for the flow system, which is what we have here. We developed one-dimensional elements and then the equations to define two-dimensional behavior. We did that yesterday. And from that, we've been talking a little bit about really the mechanics of how to better make those elements in line with industrial methods that are used, say, in COMSOL. So the isoparametric methods we've talked about are the standard way of looking at COMSOL, and we'll pull up COMSOL to be able to look at that, not now, but sometime in the next little while, to show that's the case. So those are the industrial standards. We don't have to worry about that. I think we should concentrate more on, if we want to look at some flow problems, we said before that the essence of flow problems is not necessarily the steady state, which is all that we've looked at so far, but it's also to be looking at this transient behavior. So certainly when we look at fluid flow and transient behavior in aquifers, we're also interested in being able to understand how that transient behavior in aquifers would affect deformations as well, which we cannot do yet because we haven't got the background for it, but that's ultimately where we will end up trying to go. And so to be able to do that, to be able to look at these second parts here, then we need to look at some additional concepts. And so we need to go back a little bit to the derivation from the Galerkin formulation that we talked about last time, not to rederive it, but just to borrow from our understanding of that. And we'll use that to be able to put together the system of equations that will define transient behavior. And that's what we'll do. So that's our plan for here. And so let's forge ahead with that. And so this is kind of the outline of what we'll deal with. We want to deal with transient behavior. So until now, what we have done is we have dealt only with these two terms here, and this has been ignored. So it's just been a linear system of equations that we've been solving. If you like, we've been solving AX equals B. Typically the way that mathematicians tend to write this. And if we want to solve transient problems, then we need to be able to look at the so-called, in quotes, mass matrices. And they're referred to as mass matrices because the finite element method, as we mentioned yesterday, was really developed for looking at structural mechanics, for looking at flight structures or, say, buildings in earthquakes. And when you shake a building in an earthquake, it has the inertia of the system is the mass of the system, which is resisting its movement. And so the analog to that for the flow problems is also mass matrices, which come logically out of the equation that we're dealing with. So if you remember the expression that we're trying to solve, it is something like the second order PDE that we're trying to solve looks something like this. dy squared times hydraulic conductivity is equal to some parameter specific storage and the change in head as a function in time. So far we've ignored this right-hand side, which we've put identically equal to 0. But when we derived the matrix relationships for this yesterday afternoon, then we actually did include this. And you remember that the outcome was something like equation 1, where we've spent all our time so far dealing with this conductance matrix, or conductance term, a matrix which includes the values of heads. We've ignored this uniform distribution of flux. We've dealt with the value of the other boundary conditions. And what we haven't dealt with is the magnitude of this term here. And so there are two parts of this term that are important to us. The first part is this so-called, this is what we'll refer to, for want of a better term, the mass matrix. We could call it the capacitance matrix because that's really what it is. It's a capacitance of fluid that comes out of the system or is able to absorb fluid into the system. And there are two portions of this. One is this mass matrix on its own, and the other one is time derivative. This term here, which operates on the head. And so there are two things that we need to figure out how to do. One is we want to know exactly what the form of this mass matrix is, because that's one of the parts of this extra expression. And then we have to figure out how to do the time stepping with this time derivative, because we will have to integrate this in time to be able to solve the system. So those are two separate things that we will attempt to do. So we'll do the first thing first is to figure out exactly what this matrix is, this mass matrix. So I guess this component down here is saying exactly this. We have to do two things. Figure out what the mass matrix is first, and then figure out how we solve these equations now, because the equation clearly is no longer going to be something of the form ax equals b, because we have a term here that defines it in time, but we can only really solve systems which are ax equals b. So what we need to figure out in the second term is how we make this equation with this time derivative into something that looks like this, so that we can solve it straightforwardly using the methods that we've talked about already. So that's our task. First part is to figure out what the storage matrix is, or the mass matrix. We know exactly what the form of this matrix is because we came up with it yesterday. We know what the shape functions are, and it's actually much easier to determine than this conductance matrix, as you can imagine, just because this is a simpler matrix. We just define these shape functions as we did before. So I think the way of doing this is in two ways. Let's do it two ways. We can form this mass matrix using just the straightforward integration that we used yesterday to get the conductance matrices. And we can also use isoparametric methods to do it as well. And it's a relatively fast calculation to do the second one. So let's do the first one first. A constant multiplied by these I guess should be underlined because they are matrices. We know that from these manipulations that the change in volume is equal to, dv is equal to dx, dy, dz. We know that if our element is aligned along the x direction, then these two, then we can take these two out because the integral of dy dz is just equal to a if this is a constant area along the length of this. Right? So if you draw this in 3 dimensions, the element would look like this. This would be the area of the element, and it's just constant. And so this is what we've done here. dv has gone to this and this. And that's just the new element we have. We have to choose some shape functions. We know that our requirements are 0 at the node in question, and 1 at the node in question and 0 elsewhere. And so if we use these 1 minus x over L and x over L, we can quickly check whether they're good enough for us. So if we choose, for instance, node number 1, we use x equals 0, this magnitude will be equal to 1. That's what we need. X equals 0, the magnitude at this point is 0. So it satisfies it for this one. So simple that we can do it for number 2. If we choose this node, x is equal to L, then 1 minus L over L is 0. So it's 0 at this point. L over L is equal to 1, and so it clearly satisfies our condition. And actually, if you look at these shape functions, you know exactly what they look like because we've looked at them before. They look like this, and they look like this. This is x, this is L, this is 0, this is the value of b, if you like. This is 1 minus x over L, and this is x over L, which is equal to b2. So probably doesn't hurt to repeat these things. So they're just these linear shape functions. Just like the 1 over r, I mean the r shape functions, but they're just written in terms of x. So we know what these shape functions are, so we can put in B transpose, which is this. We can put in B, which of course is this. We can multiply them together. We have terms like 1 minus x over L times 1 minus x over L, which is this term here. We have terms like 1 minus x over L times x over L, which is this term here. And so you can see that in this we basically have two different forms of terms, one that looks like this and one that looks like this. And so we just have to do these integrations with respect to the missing value here, which is off the screen, but of course this is x here. And so let's just do that. So 1 minus x over L, if we multiply it out, we end up with this expansion. So you integrate the 1 goes to x. 2x over L must go to x squared over 2x squared over 2L. And we lose these. This must go to x cubed over 3L squared. And so this. And if we substitute in the limits for these, they're going to be pretty easy to get for the 0. Ends up being L squared over L, which is 0. These cancel out. And L cubed over 3L squared, which is just L over 3. And so the value of that is a third L. So those are the terms that go on the leading diagonal, here and here. And if we do the expansion for the other term, which is this is just x over L times x squared over L squared, this term here. Again, do the integration. What's this going to be? This is going to be x squared over 2L. This is going to be x cubed over 3L squared. And again, if we make the substitutions, the 0 is going to give us nothing. The L is going to give us x squared over L divided by L, which is L over 2, which is this term here. And the L here is going to give us L cubed over L squared, which is L over 3, which is this, which I guess multiplied this both top and bottom by 3. We have 3 over 6 minus 2 over 6, which is 1 over 6. So, simply that. So we have this value here, which is this, and those are the terms that go on the off-diagonal terms. Both positive now instead of being negative. And so if we write out the form of this, we have the cross-sectional area, the constant, the specific storage of the element, and we have the length here. And so it's at least instructive to write it out in this way. It's perhaps also useful to write it, let me do it this way, to write it as specific storage, area, length, multiplied by the terms in brackets. So a third, a sixth, and a third. And the reason for writing it out that way is that you see that this term here is just the volume of the element. So the interesting thing about this expression for the so-called mass matrix, or the capacitance matrix, is B transpose B, the shape functions multiplied by each other. When you do that integration, this integration is merely the volume of the element, which is interesting. So it comes out that, I could write that out here, B transposed B dV is just equal to the volume of the element. And that's what we have here. And so that's curious that we have that. So we just have, we're multiplying a volume of the element multiplied by the storage. And the other interesting thing is that if you look at the values of this, if we do what we did last time, remember yesterday we took the conductance matrix and we added all the terms on the rows and all the terms in the columns. They all added up to 0. Here that's not going to be the case because there's no negatives in here. But if you add a third to a sixth, you end up with a half. So the value on this top part is a half. If you add a sixth to a third, you also end up with a half. And if you add those all together, if you add all four terms in the matrix, you end up with 1. And this will always be the case for this. So really what physically it's doing is it's taking this storage and it's partitioning it around the nodes in some certain way that allows us to be able to distribute the storage between the nodes. And it's at the nodes, localized at the nodes, that when we get changes in pressures, that will be the release of water that drives the transient part of the equation. So that's one way to think of it. The other way to think about this, and I guess I haven't done a very good job of opening up these blank pages. Let me do that, because I quite like doing that. No, it has to be. I can't write on it if I do that. Don't do that. So, yeah, okay, let's do this. So what does this physically mean? Let's play around with this a little bit, because I think it's useful to do that. I think it's 2.5, right? Or is it 2.6? Doesn't matter. It's 2 something. So what does this say? We have an expression that basically is saying something like d2h dx squared plus d2h dy squared multiplied by some coefficient, which is hydraulic conductivity, is equal to specific storage times the head change. This term here ends up being something like this integral b transposed b dv times specific storage. So that's what this term here is. And it's multiplied by a change in head as a function of time. So this is this overall term on the right-hand side. And at least for this two-dimensional case, one-dimensional case rather, we have this behavior here. And we can think of this, since this expression here, if it's written out, the right-hand side of this has to look something like you've seen this many times. Whoops, H1. And this is equal to Q1 and Q2. These are the fluxes out of the system. Getting a bit crowded, I realize. And so physically, what does that mean? It means that when we solve this problem, if we have different heads at different ends of the element, there's some fluid throughput through the system. But let's say if H1 is equal to H2, then that's what we did yesterday. If H1 is equal to H2, then this equals this, and so there's no flux coming out of Q1. There can be no flux coming out of Q2, and so there's no flow in the system. So what does physically the storage mean? The storage we could write out the same way. So we could think of it as Q1 and Q2. And we said that it's equal to some coefficient multiplied by a volume multiplied by it's easiest to do it this way, is it? Maybe? No, I don't do it, sorry. So it was a third, a sixth, and a third. And this is H1 and H2. And I suppose if we want to be true to this, this would be however this changes as a function of time. The head changes as a function of time. So not the fact that it's changing between element node 1 and node 2, but maybe it's going up and down uniformly. And so the physical meaning of this, you can think of this as, what is it? So say we change the head at node 1. What does that mean? So if H1 goes to H1 minus delta H, some small change. So this is node 1. What does this physically mean? It means that we'll get a flux coming out of the system, and that flux will be equal to whatever this coefficient is, this volume. This is just 1 over 3, 1 over 6. I guess that's exactly what it is, times delta H. So in other words, if this is equal to some value, and I suppose the other thing is that H2 goes to just H2, it doesn't change. So in other words, if we change the value of the head at this particular location, what happens is it pushes a small amount of water out of Q1, which is this amount Q1, and it also pushes an even smaller amount of node 2, Q2. So in other words, the head goes down only at this one node, but it squeezes fluid out of both of the nodes. It squeezes the most out of this by a factor of 2, twice as much out of here as it does out of this, but that's physically what the storage means. So the head goes down. As a result of the head going down, it squeezes the fluid out. Does that make sense in terms of what's going on? Why does it squeeze fluid out if the head goes down? Well, the head goes down, then the effective stresses increase. If the effective stresses increase, so usually the assumption in an aquifer is that the total stresses are the same. So if the fluid pressure goes down, that means that more of the load is carried by the effective stresses. If the effective stresses increase, the reservoir or aquifer compacts. If it compacts, it squeezes fluid out. That's one of the effects. The other effect, which is included in specific storage, is that if the pressure in the fluid goes down, then the fluid also expands, right? If you compress a fluid and then you release that compression, it will expand. And so if you drop the pressure, then the fluid will also expand, and as a result of expanding, there'll be these two effects. The aquifer compressing as you reduce the pressure by effective stresses increasing, and also the fact that the fluid volume will expand because you're reducing the pressure. Not so important to know that. But in this way of looking at this so-called consistent mass way of looking at things, it means that in this matrix with this distribution of these terms, it means that if you drop the head or the pressure at one node, it squeezes fluid out from both nodes in the system, or all nodes in the element, however many nodes are. The other opportunity we could do is we could say that let's not do it that way. Let's choose that if we drop the head at this particular location, so in other words, we drop the head at this location at node 1. So instead of allowing it to come out of this node as well as this node, we'd like it all to come out of this node only. And we'd like the amount that comes out of here to be 0. So one way to do that would be to take the amount that would come out of this node and just say it's going to come out of here. And so to do that, what we would do, I suppose, well, not I suppose, is we'd add this 1/3 and this 1/6. We'd add together, and we'd put it at this point. So in other words, it would be this. Q1, Q2. The expression would equal to specific storage. The volume operates on whatever the value of H1 and H2 are. It really changes in H1 as a function of time. So it'd be over a time step. And so if we wanted to make sure that all of the stuff comes out of here, including this, we just add these two terms together and put it in this location. So this would be 1/3 plus 1/6. And 1/3 plus 1/6, of course, is equal to 1/2. And likewise for this, we do the same. We take this and this. We'd add these two together, and we'd put it at this point here. And this would also be 1/2. The so-called lumped mass. Approximation. If, yeah, there's a negative in there. So if the head goes down, it would produce fluid. So this just means that this flow rate would be into the element. Yeah, you're right. So if the head goes down, then if pressure goes down, effective stresses increase. If effective stresses increase, they squeeze the aquifer and they produce fluid. So if this goes down, this should be positive. So there's a negative sign in there. Are you worried about the sign convention? Not that's too much information for this time of day. I'm not sure we've necessarily agreed on a sign. Have we? Oh, well, actually, we can tell what the sign convention is from this. So we know that Q is equal to Q1 is equal to AK over L times H1 minus H2. If H1 is larger than H2, I'm just going to rationalize it. This is H1, this is H2. This would be positive, this is always positive, and this would give a positive Q, and so in must be positive. Yeah, just by rational, it must be, yeah. And so this should be consistent in some respects. So I think that's right, right? If this is larger than this, then the flow has to be in this direction. The flow is in this direction, then has to be in. So this is definitely positive from this calculation, so in must be positive. And so if this case is that the head goes down, so H1 is negative. This is going to be a positive matrix, I'm pretty sure. And so a negative head gives a negative Q, and a negative Q means it's squeezed down. Yeah, so it works out. Yeah, good point. I'm surprised I could actually do that on the fly, actually, this time of day. But yeah, so that's the sign convention. So Q in is positive, to answer your question. And so this lump mass approximation is just a way of making it, taking this distribution of storage, which must be overall the storage of any given element, total storage of an element, storage, of any element has to equal the volume of the element times the specific storage. That's it. And so really, all that we've done in terms of these, the manipulations, is we've chosen a way to distribute it. In one way, we've distributed it largely at the node where the pressure goes down. That produces most of the fluid, but some other fluid comes out of the other location. And in this way, we've just chosen to lump those two terms together. And so that if you drop the pressure or head at this location, fluid comes out of this node only, because this term is zero on the off diagonal. And that's our way of approximating it. So that's useful for us to think about. We'll use that a little bit later. What we'll find out is that there are some advantages of having a matrix which has only terms on the leading diagonal, because it makes some of the calculations much easier to do. And it actually makes them somewhat more stable, as it turns out. So not only is it simpler to do, actually the results sometimes are better. Okay? So that's what this lump mass is here. And so we have this. And I think this makes the same point, that the total mass, total storage of the element, this really shouldn't be mass, it should be storage, I think, is equal to the volume of the element multiplied by specific storage. And so that's the sum of these. So that's one way of doing it. So we started on the hour, so we need to finish a quarter after. Okay. And so we could do this. Yeah, let's do it quickly. So we've got these matrices for doing the integration in the way that we normally have. Let's very quickly do an isoparametric case, because it's perhaps easier to do it for this than it is for the two-dimensional one. So what do we need to do? We need to, there's a lot of crossing out here, but let's go with it anyway. So this is our normal storage matrix for the same problem, which is this. If we want to do it not in global coordinates, we want to do it in local coordinates, then it's changed with this latter term is just manipulated to change it from this, which are Jacobian, same matrices. The integration, instead of being over the length of the element from 0 to L, is now from -1 to +1. This is the local element, looks like this. And we need to figure out exactly what those components are. We know we can choose shape functions, so the shape functions we've now chosen are actually the corollary or the equivalent of these. They look the same, but they're defined not in terms of x, they're defined in terms of r. And so the half is outside, it's 1 minus r, 1 plus r. And they look a bit different because the 0 point of the coordinate system is in the middle, as opposed to the 0 point here being at the node number 1. So that's why they look a bit different from before. We know, for instance, that the Jacobian in this particular case is equal to L over 2. We know that by inspection. We could also, if we wanted to, calculate it from just rate of change with respect to r of x. If we input this value as x is equal to b times the nodal values of x, then we end up with the derivatives of the shape function matrix, which we've called b prime times x. So the derivatives of this will just be -1 and +1 times a half. So this element here, b prime, is just going to be equal to a half of the ddr in this, which is -1 and +1. So, which, if you substitute this back in for the coordinates, you get exactly this. This is essentially equal to x2 minus x1 over 2. That's what this comes out to be if you just multiply it by the nodal values. Get that by inspection. And to be able to put together this matrix, we need B transpose B. So I won't write that out, but if you use these values for the shape functions, you end up with terms like this. Get rid of that. Get rid of that. Again, you have one term on the leading diagonals, which looks similar, terms on the off diagonals, which look similar. If you do these integrations using numerical integration, which in this particular case, we could calculate exactly what quadrature we'd want to use. What quadrature we want to use. We know that we have terms in this which would be the function of r is at least r squared. So the order of the equation k is equal, bad choice of term actually, we used that before as k. K is equal to second order, it's a quadratic equation. So to be able to represent that, can we use n equals 1? First order, 1 point quadrature. Remember the expression is 2 times n minus 1. So n is equal to 1. So this is 2 minus 1 is equal to 1, which is less than this order. So we can't use first order. If we use 2 point quadrature, then again 2 times n would be with n equals 2 minus 1. 2 times 2 is 4 minus 1. This is equal to 3. I guess, let me just write this out. This one is equal to 1 and can't work. This one is equal to 3, which is larger than the order of this. So this will give you exact result for at least a cubic function. So this will work for a cubic function. This would work only for a linear function. And this is a quadratic. so midway between them. So we have to use at least 2-point quadrature, which I think I say exactly here. And if I won't do it, but if you end up going to do that and integrate it, you end up with, so this is 8 over, this term is 8, it's 2.66, but I guess it's also 8 over 3. Right? So 2 is 6 over 3, 7 over 3, 8 over 3. This is 4 over 3. This is 8 over 3. And this is 4 over 3. And so by way of doing this, this 8 then cancels out with this to give a third. This 8 cancels out with this to give a sixth. And this cancels out again to give a third. And this cancels out to give a sixth. So even though we've calculated these magnitudes numerically, you can see that they're really quite accurate. They're 2.66 recurring. And they're the exact numbers that we had before in the calculation we had for the lump mass system. So in other words, they're exactly the same as these values. And of course they should be, because as we've done nothing different, we've just we've mapped it and we've evaluated the integrals in a slightly different way. We can lump it in the same way as we did before, and that gives us the ability to be able to figure out what's going on. So that's kind of the first part of what we need to be able to do. So we said that when we deal with these problems, if I scoot back to the back, the beginning, there are two things we need to know. We need to know, first of all, in calculating this component, what the S matrix looks like. And it's something like specific storage times this integral B transpose B dV times rate of change with time of nodal values of head. And so we said that the first thing we need to figure out is exactly how to calculate this. And that's exactly what we've done so far. So we've figured out how to do that. And we've done a couple of examples for these one-dimensional elements. And so now, if we want to solve this, we can only ever solve this as a linear system of equations. And so we had to figure out how to be able to manipulate this into a way in which we accommodate this time derivative into something that looks like A times X equals B, which is what we were able to solve. So that's the second part. I guess I said we'd talk about that afterwards, but I guess it's in this sequence of notes. So let's figure out how to do that. We know how to get the lumped components. So the basic idea is this. What we can do is at any particular node, we can take a value of the head at that particular node at time t. And at the same node, not in space now, but at the same physical location, we can look at what the magnitude of the head would be at some later time, t plus delta t. And it will change between those two. If we want to be able to use that, if we assume that, for instance, the change in head between those 2 points in time is linear, it varies as a straight line, then I guess we can do a couple of things. We could, for sure, we could say something like the rate of change of head as a function of time. We could also write as a finite derivative. And so if we are measuring the head at time t and sometime t plus delta t, then clearly the difference between those magnitudes is some length delta t. And just by convention, we can write this partial differential out as the magnitude of head in the future minus the magnitude of head in the past divided by the time over which it happened. So it would be head at time t plus delta t minus the head at time t, which is just this difference here. And divided through by the length of time it takes for that to happen. So that's one way of being able to define this. We said that we could do it for a single node in the system, but there's no reason that this couldn't also be every single node within the system. If we had 10 nodes, then there'd be 10 values in a vector, and they'd change from one vector at time t to another vector at time t plus delta t. And so in the same way that these could be an individual number, they could also be a vector. This could be a vector, this could be a vector, and this could be as well. This would be just subtracting two vectors from each other. And these would be the nodal values of heads. So heads at nodes 1, 2, 3, 4, 5. If we have three node elements, there'd be heads at nodes 1, 2, and 3 at time t. Then heads at nodes 1, 2, and 3 at time t plus delta t. There'd be two different vectors that we can just subtract from each other. So that's one way we can think about this. The other way I guess we could think about this is that if we know the value of head at this point, we could calculate the value of head at this later point by just doing a straightforward manipulation. So the head at time t plus delta t would be equal to the head at the previous time plus, what would it be? We could write out this differential plus delta h. So this is the change in head that occurs between these two. So in other words, we start out at this, and if this value here is just equal to delta h, this term here, then we can just do what we did before. We could also multiply this by 1. And if we write it out a bit more interestingly, this is just equal to delta h over delta t multiplied by delta t. And of course this is exactly this. So those are the two things that we can get out of this. Two important equations. And they merely come out of the fact that this is a straight line relationship between this. We haven't done anything more than that. And so what we'd like to be able to do is use these relationships to be able to figure out exactly how we can march in time and solve this system of equations, which if we come back to this is this, that include this factor here. And there are two ways we can do it. We can do it by a method which is called implicit, which is the first one we'll talk about. We can talk about a second method which is explicit. And we can talk about one, I'm getting cramp in my hand, which is part way between. And we'll talk about Crank-Nicholson. Oops. N-I-C-O-L-S-O-N. Two people's names. Crank and Nicholson. Crank is a very famous person who worked on diffusion problems. Don't know who Nicholson was. There's a book on diffusion by Crank. And so we'll talk about the implicit one first. But it basically revolves around this idea that we can project things in time. And so what we could do is, I always think that if we're looking at this implicit behavior, then we can write the equations at this future time, and we can look back and be able to use this expression here to be able to define exactly how we get there. And so maybe that's a bit of a, not a very clear way of stating it. So here's the expression that we have. Conductance matrix, nodal values of heads, storage matrix, rates of change of values of nodal heads, and a flux vector. We certainly know how to get this matrix, the conductance matrix. We now know how to get this storage matrix. The only thing that's different here is that this, we haven't really said it before, but this matrix we can write at any particular time we want to. We can write it at this point here, as we said we're going to. We could write it at this point here, and we can write it at any point in between these, maybe at this time h tau, or time tau. This would be time tau, and we could write it anywhere. So that equation is exact no matter where we write it along the trajectory of this line between these 2 points. So if we do that, let's choose to write it at this point. So this value here is tau, which is equal to t plus delta t. So we're going to choose to write it at this particular magnitude point. So all we're going to do is replace this value here by t plus delta t. This is the time we write it. I guess I didn't need to write that. So this is the point. We're going to write it here. And so this is what the expression looks like, equation 2. We've already derived an expression that says how head changes as a function of time. Right? We did it for one node, but we can also do it for all nodes, which is what this is, since these are underlined. We had this expression on the previous page. This overstated dot just means dh dt, just this shorthand. This is engineering shorthand for time derivative. And instead of writing it at time tau, like this here, we're going to write it at this particular time step, in the future time step. We don't get the chance to change these because these are already provided by the anchor points. The beginning point and the end point are t and t plus delta t. So what we could do is that since we need the value of this time derivative right here, we could substitute this value right in. And that's exactly what we're going to do. And so if we do that, equation 2 becomes equation 5. The first term here is this. The second term here is augmented by this term here, which is here. And the right-hand term is still exactly as what it is. And so if we want to solve this equation, we want to know what the behavior is at this future time level as a function of the earlier time level. And so what we'd like to do is let's gather all the terms that involve h, t plus delta t, the head at the future time, together. So in other words, we can combine these two terms together, and then we can take this term off onto the right-hand side. So we'll keep all the terms that involve the future time. So we'll take all the terms that involve this time on the left-hand side. We'll take all the terms that involve the previous time, which we should know what it was because we're standing in the future, and we'll move that to the right-hand side. If we gather terms, then we have this. So in other words, this expression and this expression get added together into this matrix. And they operate on this magnitude of head. This term has gone on to the right-hand side. Of course, it's pre-multiplied by this value, so this value has to go with it. And the ultimate term is this whole term here. And so what we could think of is this system as a matrix which we'll call K star. This whole thing is K star. It has this extra term added to it. And this term on the right-hand side, we'll call this Q star. And so K star operating on the heads in the future. Q star is just a term where we know the values of the previous heads because we originally have come from there. And so if we look at this, then we basically have an expression which said we can only solve expressions that look like ax equals b, where we solve for the values of x. That's exactly what we have. We want to solve for this as a function of known values of this, and at least of a conductance matrix, which we can also put together as well. And so we have everything we need to be able to do that. So let's try doing it. So here's a simple problem, right? So what we've done is we've basically made a substitution for dH dt in terms of this linear projection. That substitution for dH dt allows us to be able to incrementally break out the parts which refer to the new time step we want to solve for versus the old information that we know, and then we can just step in time. So that's really what we're doing. So let's do a simple example again to be able to make this case. Okay. And I think we stop after that. Yeah, that's fine. So here's the idea. Very simple problem of a one-dimensional flow system. So what we'll use is two elements with nodes 1 and 2. This is element number 1. Element number 2 has nodes 2 and 3. You start off with the initial condition being that the head is uniform and equals 1 at t equals 0 minus. And then all of a sudden at time t equals 0 plus, so in other words, the beginning of our problem, when we turn on a system, what we do is we take the pressure at this node, and instead of being 1, so this is the head versus height, we're going to move it from being 1 here to being 0. And so this effect is that now the head is 0, then it will slowly readjust from this initial distribution, which looks like this, to over time it would change to look like this, to look like this, to look like this, to ultimately look like this. So in other words, we're going to set this value equal to 1 and hold it there. This is a prescribed head. We're going to set this value originally equal to 1, but change it to 0. And as it readjusts, it will give us this final behavior, will be this linear distribution of head between them. So that's the behavior we expect to see. Let's apply some properties to this. A hydraulic conductivity of 1 meter a second, a specific storage of 2 per meter. We can calculate what the units of this is per meter. And we'll use a time step of 0.1 of a second, just to be able to do it. So what are the matrices going to look like? We know that the conductance matrix is going to be equal to area times conductivity divided by length, 1 minus 1 minus 1, 1. Area is equal to 1, conductivity is equal to 1, length is equal to 1, total depth of 2, so this is just equal to 1 minus 1 minus 1, 1. So that's exactly the term that we have here. So this is the same for both of these elements here. We know that the storage is going to be what? Storage is equal to the area times the length times the specific storage. We're going to use it in lumped form, so this is going to be a half, 0, 0, a half. And so area is 1, length is 1, specific storage is 2. So that merely, I've changed the results afterwards because it was wrong, hence the scoring out. So this is going to be 1, 0, 0, 1. And that's this. They're both the same as each other. So those are the two storage matrices. We put together the system of equations in exactly the same way as we did for the steady state problem. And so if we look at this relationship, this equation that we're trying to put together. For our particular geometry, if we have two elements on top of each other, and I think this is 1, 2, and 3, then what does this matrix relationship look like? It's going to look something like a K matrix, which operates on nodal values of heads at point node 1, 2, and 3. So that's this element here, right? This component. It's going to be added to something that operates on the rates of change of the heads at nodes 1, 2, and 3. I guess these would be rates of change of those values rather than their values per se. This will be the storage matrix. This will be heads. This will be head dots. So now this is this term here. And it also has to conform to the fluxes at the nodes Q1, Q2, and Q3. So this is Q. So that's it. We know that since there are 3 equations here, there have to be a 3 by 3 matrix with 9 terms. And we can calculate what those would be. We know also that this has to be a 3 by 3 matrix. And we know that we have the individual K matrices for node 1, which will contain 2 terms. And if we look at if this is the global system, this is the local. So the local would be that you take this template, which is element node number 1 and 2, and the other local is you take this template, and again this is 1 and 2. And so you remember this indexing that we did for these elements, just in terms of the location. And we know from yesterday that K1 is going to go right here. It's going to have these 4 terms in it. This is K1. And we know if we look at K2, I might as well write it out, no reason not to. What is it going to be? It's going to be, these are local 1 and 2, but they're actually global 2 and 3. So this is 2, 3, 2, 3, and so this will actually physically go here. And it's no different from what we did yesterday. And so this will be plus y, this will be y, this will be y, and this will be y. Whatever these terms are. Actually, we know that the off-diagonal terms are negative of the on-diagonal terms, but we won't worry about that. I suppose we also know now that the storage matrix, S1, what does that look like? Again, it has to be 2 by 2. We're going to use this lumped storage term where we have only the terms on the diagonal. And so when we put that in here, we'll end up with these locations. And when we look at the storage for the other one, it will also have terms only on the leading diagonal because we're going to insist that it's lumped. And again, the indexing of this will be 2 and 3, 2 and 3. And so these ones will just go on this component here. This will be plus y, and this will be y. The off-diagonal terms will be 0. And so we know exactly what these will look like. And so I thought it's useful maybe to draw it there or write it out there because it's going to get crowded on the other component. But that's basically what we're going to do, is we're going to use the same indexing technique we used last time to be able to fill out these elements. And you have it written down here somewhere. Here. So, whoops. So that's exactly what we have here. This one here goes here. This would be 1 in this case. And this one here goes again over here. So this is 1 plus 1, which gives you this 2. It's just the amalgamation of those. Likewise, we take this. This is the first one that goes here. This is 1 and 1. The second one goes on top of it and supplies the extra value to this point. And so that gives us at least the form of the expression that we're going to deal with. What else do we need to do now? Well, we probably need to manipulate it a little bit. What do we know about the boundary conditions for this? Well, we're going to start off with a head here, H3, which is known. And we're going to start off with a head here, H1, which is also known at the when we start the program. We're saying it starts off at 1, everywhere 1, but then it goes to 0. And so we know the magnitudes of head at both nodes 1 and nodes 3. And so since we know the values of heads, what we can do is we don't actually really need those expressions, but we can modify the boundary conditions to be able to do that. So what we need to do is we need to take the values of H1 and of H3. We multiply them by the magnitudes on this curve here, and we take them off to the left-hand side. So H1 times 1 is 1H1, and we subtract that from both sides, we end up with minus H1 here. H1 times minus 1 gives us minus H1, and if we add H1 to both sides, then we end up with this term here. So we just rearrange for the boundary conditions. We do the same once we've done it for H1, we do it for H3. So H3 times minus 1 is minus H3. Add plus H3 to both sides, you get rid of this term, and you end up with this. And H3 times H1 gives you plus H1. Subtract H3 from both sides, and you end up with this term, and you're left with this. We don't have to worry about these. Actually, what we're going to deal with is we only going to deal with this middle equation. We only have one degree of freedom in this system. Oops, I can't draw a straight line very well. And so we only need to actually deal with this middle equation. This is the one we need to deal with. Yeah, go ahead.
H3 is equal 1, but in the matrix, H3 values are substituted by 0.
Oh, yeah, just because we don't need them anymore. Because we've so this is H3 is 1. So if we take this value and multiply it by this, then we end up with a value of 1H3. And if we subtract 1H3 from both sides, then we end up with 0 here and minus H3 on the right-hand side. So all we're doing is we're multiplying these two together and then subtracting that amount off both sides. So I think you're right, it's perhaps not the best way to show this, but we don't care about, actually right now we don't care about this bottom equation. We don't care about it at all. So the terms in the matrix, we don't care. We're going to need to take account of what these terms are. Actually, we don't care what these are either. We're only going to worry about what H2 is. And we've taken all the relevant values of H1 and H3 off to the right-hand side. We didn't have to do this. We only needed to do it on this middle equation. Okay. All right, so now what do we have? So what we have is we have one component here, because we're only looking at this middle equation. We only have H2, and we only, in this equation, have H2 here. So I suppose we could write this equation, if we wanted to, as 2 times H2 plus 2 times H2 dot, which is this term here, is equal to Q2 plus H1 plus H3. So that's all that we have left out of this. This is So we're going to take these two together then and write them slightly differently. We're going to take these two, we have a value of k, we have a value of s, and so what we can do is we can make this k star matrix, what we call this. So the value of conductance plus 1 over the time step times the value of the storage matrix, and multiply it by this. So that would be, this is k, so this would, we only have one term, this is 2, this is s, we only have one term, this is also 2. We have a value for delta t, we said that was 0.1 seconds. And this is this k star matrix. And this whole term here on the right hand side is almost q star. So what do we have? The line through this, no different from before. We have two elements. We said that the flux in this middle node benefits from the stuff coming in from one element and the stuff going out into the other element. They have to balance each other. So the net values of Q have to be 0. So hence this term here, this is 0. Then we're left, actually if you look at this on the next page, so there's 0. Oh no, sorry, yeah, do something else, forget that. So in other words, this is 2 plus 1 over 0.1 times 2, so the value of k star is equal to 22. So that's a constant. So we've dealt with this part. So now we know exactly what the value of k star is. It's 22 in our particular case. So what is the magnitude of this? This term is equal to the value of this load vector plus this extra term here. So let's go ahead and make that. And so the value of this load vector is equal to Q2, which is 0, H1 and H3, which are the terms here. But we also have to add, so that we make this into Q star, this term delta T over S times whatever the value of the head from the previous time step is. So this is 0. What is H1? H1 is the top one, which is equal to 0. H3, as you pointed out, always stays equal to 1. And the storage term from here is equal to 2. And this term here is equal to 0.1. So this is this expression here. And so the initial condition that we have when we start the system is that initially the head at this point is equal to 1 before it changes. So the value of this head at time t equals 0 minus is this. That's the initial value that we'll use for here. And so that's here. And so if I just pull this down, we have a value for k star, which is 22. We have a value for q star, which is 1 plus 20 times h2. It's the true value. And so if we put this in here, and if we put this, I guess it doesn't go across sheets, down here, then we have this expression here, at least for the first time step. If this starts off as equal to 1, then this really is 21, but it's probably better if we write it in this form because this will change with time. And we have a relationship. If we divide 21 by 22, we end up with the value of the head at 0.1 seconds, which is 0.9545. And so what we can do is we can write an expression which now solves this, which is this expression. And the recursive expression, I guess, this is always going to be 22. This is what we're solving for. this term here, I guess we said, is always equal to 1 plus 20 times the value of h2 from the previous time step. And this is the recursive relationship that we need to solve. So on the first time step, we put in a value of h2 as being equal to 1. But then on the subsequent time steps, we update it whatever the new value is. So I guess, yeah. And so if you rearrange this equation here, this is the final expression, the recursive relationship you get. So the head at any time is equal to 1 over k star. K star is 22, we said. And this here, so this is just this relationship written out to be able to solve for the value of this parameter. And so we can merely match in time. And so we have a 3-node system. The bottom node is set at 1, ahead of 1. The top node starts at 1, but immediately goes to 0, and so we ignore that. And the middle node must start out at 1 as well. And so if we start this out at 1 for the first time step, then we get the first result at the next time. And then if we keep on resubstituting the revised value of this head, we're able to march through time. And that's it. And so this isn't a very good graph, but it serves to illustrate the purpose. We've chosen to use a value of 0.1, time step of 0.1. If you go through this, do we have it? I guess. The first time step is equal to, is 0.9132 at t, oh, it's the second time step. First time step is 0.95. So if you look on this plot, first time step is 0.1. So yeah, this is about right. This is the first time step. It's about 0.95. The second time step, well, I can't really scale logarithmically too well. So 2 times 2 seconds would be roughly here, right, I think? And so if you go up here, then this would be the value. The magnitude, is it less than 0.9? Didn't look like it was. Oh yeah, no, 0.913. So bottom line is that this is the behavior that we get from solving this equation. If we use 0.1 seconds, then we get this trajectory, this particular behavior for this middle node. If we use a hundredth of that, then we get this exactly the same graph, but defined with many more points. If we use a much larger time step, 10 times larger, then we get a different response. The first value has to be at only 1 second, which is here. If we use 2 seconds, then the first value is at 2 seconds, and they're different graphs. And so that's important to realize that. And the comments at the bottom of this figure, I will say, but you have them today. There are probably 3 or 4 comments. One is that we've chosen a method which is unconditionally stable. It turns out it will always give us a good result, but you see from these that the results are not always the same. So even though it's unconditionally stable, it will only give us the right result for our mesh if the time step is small enough. So that's the first part to note. It'll only give us a good enough solution for our particular mesh if the time step is small enough. And in that case, if you use a hundredth of a second, or a thousandth of a second, or a 10,000th of a second, you'll end up with exactly the same curve. For all that extra effort in solving 10 times more time steps or 100 times more time steps, you will still get the same curve. So that's one important thing to realize. The second one, which I think is equally important, is that the fact that these are on different trajectories are because the discretization in time, the time step of 0.1 versus 1 second versus 2 seconds versus 5 seconds, is how it's discretized in time. So when we solve these systems, it matters not only how we discretize in time, but how we discretize in space. In this particular problem that we're solving, we drew this picture of what this solution should look like, and we said that it should start off with a head that looks like this, ultimately it should look like this, and in between it would have this curved profile as it goes from one to the other. But in the geometry that we've chosen, it clearly only has one central degree of freedom. So the path that this can take can only go from looking like this to looking like a straight line here and a straight line there, a straight line here and a straight line there. And so how well this represents the real physical system that we want to represent that would behave like this depends on how well we discretize it. So with only one central node and two top nodes, the solution that we get might not be very good. If we use a whole bunch of elements in this to be able to represent this behavior, then presumably we would get the true behavior of this physical system. And so that's a key point. So this is a spatial discretization of the system. Discretization is just a fancy word of how you divide it into time. And this represents the temporal time description, discretization. And the only point I'm making is that we get a uniform solution for any time step. So 3 points. One is we always get a solution, and it's always a stable solution. So that may fool us in the absence of any other information, that if we run it at a time step of 2 seconds, we're getting the right result. Clearly we're not. If we run it at less than 0.1 second, we're getting a reasonable result that is always the same, even if we use a finer discretization. The question I had yesterday. So that's fine. But this temporal discretization is fine, but now the spatial discretization that we're getting for this really doesn't represent the real case we think we are. And so only by dividing it up into a much finer grid and seeing what the behavior is at this finer grid will we be able to be sure that we're solving the real physical problem that we think about. And so that's a cautionary tale. And the way that you can always check whether your mesh is working the way you want it is, you run a physical geometry of your problem, you run it with a mesh, and a time step, you get a result. You run it at a shorter time step, and you see if you get the same result. If you do, that's great. Then you make the mesh finer, and you see if you get exactly the same result again. If you do, you have a solution. If you make the mesh finer and you get a different solution, then you don't have a fine enough mesh to be able to solve your problem. And so that's the process we have to go through to be able to do that. So this is a useful exercise, I think, to be able to illustrate that. So that's the lion's share of talking about time discretization.